Hello, welcome to another Chemistry 30 video. What's going on? It's Mr. Walton here. We had some good questions about how in my notes package, one of the examples did not match up with the video from last semester. And so I'm just going to make a new video about that right now, if that's okay with you. So here's my current notes packet. And what we want to do is we want to kind of go over this example in a little bit of detail so that we can all kind of be on the same page. So we can use the oxidation numbers to balance equations in acidic or neutral solutions. If one element gained electrons, then another element must have lost electrons. So step number 1, assign oxidation numbers and identify the atoms or ions whose oxidation numbers changed. Let's go through this. So we have permanganate reacting with dinitrogen tetraoxide, and it's producing nitrate ions and manganese ions. This is an unbalanced equation. And what we're doing, we're balancing the following reaction in an acidic, acidic solution. So what that means is we have both of these entities at our disposal. We can either make them or we can use them up. Either one of these could be a reactant or they could be a product or whatever, okay? So we're going to assign oxidation numbers here and we're going to go ahead and get this started off. When I look at this equation, the easiest thing for me to do is just say, okay, oxygen minus 2, oxygen minus 2, oxygen minus 2. Ion, monoatomic ion, plus 2. It's just whatever the charge is. So now you have to figure out what some of these oxidation numbers is. And hopefully, I'm crossing my fingers, you can't see, but hopefully you kind of remember how to do this. If the whole charge on this thing is minus 1, and there are 4 negative 2s, 4 times negative 2 is negative 8. So this is negative 8. And we want to cancel out all of it except for minus 1. This has to be plus 7. Go back and look at the oxidation numbers video if you have any questions, or let us know during office hours and stuff like that. Okay, so for oxygens, again, that's minus 8. That means we need to have a total of plus 8, and plus 8 divided by 2 is plus 4. Perfect. Here, that's minus 6, and we want to cancel out 5 of the minus 6, so plus 5. Perfect. We've assigned our oxidation numbers. Now, let's see what's gaining and what's losing electrons. Manganese in the permanganate is going from plus 7 to plus 2. Now think to yourself, is that getting more negative or less negative? Because electrons are being transferred here. Looks like it's becoming more negative. Plus 7 to plus 2. That's more negative, so it's gaining electrons. How many electrons? 5 electrons per atom. And because there's only one manganese in the whole formula, 1 manganese, so 1 times 5 is 5 electrons in the formula unit. Perfect. So this whole thing, the whole kit and caboodle, gains 5 electrons. Here, nitrogen's going from plus 4 to plus 5. Is that more negative or less negative? That seems like it's less negative. So it's losing electrons. 1 electron per atom. This nitrogen right here goes from plus 4 to plus 5. It's losing one electron. Is there only 1 nitrogen here? No, there's 2 nitrogens. So 2, and they each lose 1 electron. If you had 2 nitrogens and they each lost 1 electron, 2 times 1 is they would lose 2 electrons in total in the formula unit. Perfect. So if this thing's gaining 5 electrons and that thing's losing 2 electrons, can this gain 5 if that thing loses 2? No, it can't. So what we have to do is we have to figure out how we can balance it so that they lose and gain the same number. We're going to use the lowest common multiple. The lowest common multiple between 5 and 2 is 10 moles of electrons. So what that means is 10 moles of electrons will be transferred from N2O4s, plural, to MnO4s, plural. Well, how can we do that? Sorry, we kind of skipped a bunch of steps. Step 1, assign oxidation numbers. That's what we did. Step 2, do per atom, the change in electrons per atom. Step 3, do the change in electrons per reactant. Sorry, that means per formula unit, So we're going to move on to the next page here. I just got to kind of copy some stuff down. Okay, so what we have to do is we have to figure out, okay, the lowest common multiple of electrons is 10 moles of electrons. How can this thing lose 10 electrons? If one of them loses 2 electrons, 2 of them would lose 4, 3 of them would lose 6, 4 of them would lose 8, 5 of them would lose 10. How can we gain 10 electrons here? 2 of them would gain 10 electrons. So that's what we have to do. We have to go and we have to balance this, calculate the simplest whole number coefficients for the reactants that will balance the total number of electrons transferred. We want to transfer 10 electrons. Okay, no problem. We need 2 of these and we need 5 of these. Now, balance the products to match. So we're going to balance all of the elements that are not hydrogen and not oxygen. So 2 manganese means 2 manganese, 10 nitrogens, so 10 nitrogens. Are we okay? Let me know if you have any questions. So now the manganese and the nitrogens are all balanced. Now we want to balance the oxygen atoms by adding water to whichever side needs it more. Let's look at this. How many oxygens? I'm going to kind of cut my reaction in half between reactants and products. How many oxygens are over here? Well, people want to say 8, or they want to say 20 because there's 8 here and there's 20 here. But there's 8 here and 20 here, so that's 28. There's 28 oxygens over here. How many oxygens are over here? Well, there's 30 oxygens. So where do I need more oxygens? I need more oxygens on the reactant side. I'm going to add 2 waters. That's added another 2 oxygens, so now I'm at 30. So that's good. Perfect. So our oxygens are all balanced, okay? Now we have to balance our hydrogens. We have to figure out how many hydrogens are on the left-hand side, how many hydrogens are on the right-hand side. Well, I see 4 hydrogens. Nothing. Okay, I see 4 hydrogens. So we need to add, because this is in an acidic solution, we can just write 4 hydrogen ions at the end. Okay, so I know we're balanced using the law of conservation of mass. I know all of the elements, there's the same number of elements on this side as there is on this side. But the last thing we have to do is we have to balance our charges. We have to just make sure our charges are balanced. Let's look at all the charges on the reactant side and all the charges on the product side. So 2 times 0 is 0. 2 times -1 is -2. 5 times 0 is 0. So the total charge on the left-hand side is -2. How many charges are on the right-hand side? Well, 10 times -1 is -10. 2 times +2 is +4. 4 times +1 is +4. What does this side add up to be? This side's -10 plus 8 is -2. So this side is -2. This side is -2. Boom. We're balanced. Woo! That's what I'm talking about. Okay. So our reaction is balanced using the law of conservation of mass. That's why we balanced all of the non-hydrogen oxygens and then the oxygens and then the hydrogens. But then we just want to go back and double check double check that the law of conservation of charge still works, right? We want to make sure it still works for our reaction. So I'm just going to get rid of that. And perfect. So this is now our balanced chemical reaction. And it's really hard for me to draw on this thing. There we go. Perfect. That's our balanced chemical reaction. I don't know. Hopefully that helped. And if it didn't, then let me know. But if it did, also let me know. Whatever. Okay. Let me know if you have any questions. Put your questions in the Google Doc or talk to Newton, myself, or Zelinsky during the office hours listed on Google Classroom. Thanks. Bye.